Hi, hello guys. Look, this is a further continuation of those boilers, and I think after this one we're gonna do three advanced ones. But these are just examples from a steam plant book by Mr. O.D. Bryan, and he said, and please man, maybe when I start to demonstrate by calculations, you will see exactly what's going on. It says a steam is generated at a pressure of 1900 kilopascals and 250 degrees Celsius, and at a tempo of 6,500 kilogram per hour. Now, or in a steam boiler plant consisting of an economizer, you are now familiar with that, an evaporator, you are also familiar with that, and a superheater. You know those components of a boiler. The supply water enters the economizer at a temperature of 37.7 degrees Celsius and leaves it at 75 degrees Celsius. Is it 75 degrees Celsius? Or I will just confirm. The dryness factor of steam leaving the boiler is 0.82. Very, very important. The fuel consumption is 620 kilogram per hour with a heat value of 38 megajoules per kilogram. And now the air is supplied at 25 kilogram of air per kilogram fuel. Calculate the following. 1. The efficiency of the boiler, the equivalent evaporation. I don't think you are familiar with that. The equivalent evaporation from an 800 degrees Celsius. The temperature of the exhaust gas at the outlet of the economizer. Actually, he made it even more easier. He should have just said the temperature of the exhaust gases. That's it. At the economizer, if the inlet temperature of the economizer is 480 degrees Celsius. 480 degrees Celsius. I'm giving you just 1 minute to write that down. While I just want to check whether is it really 75. I can't remember myself seeing 75. 75.9. Yes. 75.9 degrees Celsius. Sorry for that, guys. I don't have space, guys. I'm gonna erase this and draw our diagram, and on top of that diagram we do our calculations already. Guys, it's just that I was forced to do this problem. I'm actually from the night shift, so I hope you'll forgive me if you see that I'm not well. I don't think I'm well, but at least I can do a problem. First of all, let's draw our boiler sketch. Our boiler sketch is something like this, and then there is that pump that pumps water into the economizer there, and then the economizer hot up that water and brings it into the evaporator. Below that evaporator we've got a furnace there, and then we've got a superheater there, and then that steam is taken to go and drive that engine there. And then let's add something, guys. One of the advantages of steam is that it is used repeatedly. That's one of that's the most important advantage. You can use the steam repeatedly. Why? Only when you install a condenser. Let's say, for argument's sake, this is our condenser, this one. And then you're gonna need an extraction pump to pull that water, to pump that water from the condenser back into the hot well. Let's say, for instance, this one. Okay, it's a kisu. Like this. It's something like this. This is an extraction pump. This is an economizer. And then previously we did the other components. So why the condenser? We want to use this steam repeatedly. But the steam comes after used from that engine. There is still there's a water mixed with steam. There's a water mixed with steam, and we call that water condensate. What is a condensate? It's a condensed water. It's a change of state from gas to liquid. From gas to liquid. That gas, that steam, should condensed, but it won't condense completely. Say this is a condensate. Is that condensed water, the steam that has been used and is now converted to water? You have to add water again. Why? To make sure that steam, the gas is completely water. You've got a complete condensate with no gas. Why? Because the pump can't pump gas. It pumps water. This pump, it pumps water, not gas. So you add more water so that the remaining gas there in the condenser, it becomes completely water. Then we call that thing a condensate. And then that condensate is extracted by this pump to the hot well. That's why we add water there. We add water from the dam or from somewhere, but we add water in addition to this condensate. Right. Now, the enthalpy of feed water, let's say it's H1, is equals to what? At a pressure of 37.7 degrees. At a pressure of 37.7 degrees. Let's check. Hey guys, I'm not good with my eyes. At a pressure of 37.7 degrees is equals to what? Is equals to 158. Is equals to 158 kilojoules per kilogram. Or you can say H1 is equals to the specific heat capacity of water multiplied by the feed water temperature. Hopefully you'll still get 158 kilojoules per kilogram. But remember, we said normally in problems of this nature, we work with possibilities, interpolations. You might differ slightly from my answer and so on. Like this one, it's 4,187 multiplied by 37.7 is equals to what? 157.9. Yeah, it's 158. It's 158. You'll never go wrong with that. It's 158. Now you've got an enthalpy of feed water entering the economizer there. And then this water, it leaves the economizer at a temperature of 75.9 degrees. So we go at a temperature of 75.9 and check what is the enthalpy at that temperature. What is the enthalpy of that temperature? 79. Oh, Sekiso. You really have to see the doctor, boy. Your eyes are not good. 75.9, and the enthalpy there is 318. The enthalpy at 75.9 degrees there. Let me put it here. 75.9 degrees Celsius. The enthalpy, I'm going to call it H2. The enthalpy there is 318 kilojoules per kilogram. All right, that it is at the exit there. Now here, at a pressure of 19, let me write it in here, 19 kilopascals. At that pressure, what is an enthalpy of liquid there, of enthalpy of water? Is equals to enthalpy of water at 1900. Hey guys, this is very important to know how to read this. You go to the enthalpy chart and you check there is pressure, temperature, volume, and so on, specific volumes rather. And then there at 1900, no, it's not there, it's somewhere else. $1900, and there at 1900, the enthalpy of liquid is 897. HF is equals to 897. Remember, you are given X is equals to 0.92. But what is enthalpy of evaporation? HFG is equals to, you go at 900, is equals to 1899. Is equals to 1899. You can calculate the enthalpy of wet steam there at the outlet there. And the enthalpy of wet steam, let me write it this way. Why wet steam? Because you are given a dryness fraction. If the dryness fraction is 0 point something, then you've got you're gonna have the product of a wet steam. Only when the dryness factor is equals to 1, then you have what? A dry saturated steam. What does that mean? That steam is still produced at saturation temperature, but it contains no droplets. All the water is being converted to gas with no droplets. That's what is meant by dry saturated steam. Okay, right. And it's equals to what? It's equals to HF plus XHFG. This one is wet steam, and it is 897 plus open brackets 0.92 multiplied by 1899, and it's equals to what? It's equals to, let me say, 0.92 multiplied by 1899 equals to plus 897, 2644,08 kilojoules per kilogram. Even if you would have just go and say 2644 kilojoules, that's it. Why? Because after a comma it's a very, very small value, but it's fine this way. Normally we call this part the elementary. It's done normally from schools and universities. In practice, normally we estimate, because we are working, we are not doing this. Okay, this is the steam there at the outlet. But now, this is enthalpy of wet steam. But at 1900, what is an enthalpy of dry saturated steam? Dry saturated steam. You decrease the volume of the steam by adding more energy in order to burn more water, because you actually want the steam to be dry in order to drive an engine. In order to drive an engine, the steam must be dry. That is why we even installed a superheater there to give it more power, more energy. But at the same time also to ensure indeed that that steam is dry. Because if it's not completely dry, what's going to happen? It's gonna produce dampness. By dampness I mean there will be a condensation formed on the engine. And then remember, when the engine runs, when the engine is in operation, the air on this thing, on the engine, expand, and it means what? It means air or water. And then when that engine cools off, that water, that steam there, the remaining steam there is gonna condense. And then when it condenses, it does what? It's gonna be water, and water forms what? It forms rust, and it will even render this engine inoperative and so on. So basically we want dry steam there. So at 1900, the dry enthalpy of dry saturated steam is equals to what? Let's check. At 1900, 1900, it is 2796. There, dry saturated steam, the Hg is equals to 2796. 1900. Just bear with me, guys. I don't have my glasses. 2796, yes. Kilojoules per kilogram. This is enthalpy of dry saturated steam. That's gonna enter the superheater at that pressure. But we want this dry saturated steam to have more energy. We have to add more energy. What energy do we add? Okay, this is enthalpy of superheated steam. Entrance to the superheater is this enthalpy of dry saturated steam. But you have to add energy. What energy? This energy. Specific heat capacity of superheated steam into superheated temperature minus saturation temperature. We did this thing, guys. You remember last week we did this. The steam is wet and produced at saturation temperature, and in order to get this steam completely dry or to give it more energy, you will have to add temperature, and you are given a temperature of how much? I think 250 degree, and the saturation temperature there at a constant temperature, we will see at what temperature is there. It can't be 100. The boiler works with very high pressure and temperatures, but it's something like that. All right, it is this one. Now then that we've got this one, H soup is equals to how much? 2796 plus, let's make it even more better and practical. You don't check, but just check in class if maybe you are given. But the specific heat capacity of superheated steam is 2.1. It's 2.1. And you are given a temperature of a superheated temperature of 250. And that thing, it happens at what temperature? It happens at a temperature of 209.8. 209.8. That's the temperature, saturation temperature. And then the superheated steam is equal to what? It's equal to 250 minus 209.8 multiplied by specific heat capacity of superheated steam is equals to plus 2796. Answer 2880. 2880 say, 42 kilojoules per kilogram. So the thermal energy of this whole system, okay, this H superheated steam is equals to H4. This enthalpy of wet steam is equals to H3. So we've got H1, H2, H3, H4. So the thermal energy, the transfer of energy from here to there, that's the thermal energy. And it's equals to what? It's equals to H sup enthalpy of superheated steam minus enthalpy of feed water. This is the thermal energy. And now let's calculate the boiler efficiency. Efficiency of the boiler is equals to what? This, do it proper, is equals to mass of steam into enthalpy of superheated minus enthalpy of feed water over what? The mass of fuel multiplied by heat value or caloric value. And what is the mass of steam? The mass of steam is what? The mass of steam, van Streyer. You really need classes. The mass of steam. Let's check. The mass of steam. The mass of steam. 6.5. 6,500. It's 6,500. 6,500 per hour into enthalpy of superheated steam. It was calculated and found to be 2880,42 minus the enthalpy of feed water, which is 158. And it is equals to what? It is equals to the mass of fuel. It's equals to what? 620 multiplied by the heat value of 38 megajoules. So it's 38 multiplied by 10 to the power 3 kilojoules per kilogram. I've converted megajoules to kilojoules so that we can work with the same units. And it's equals to what? It is equals to 2880,42 minus 158 equals to multiply by 6,500 divide by 620 multiply by 38 exponent 3 closing brackets answer multiply by 100 75.1 75.1%. We must multiply by what? By 100 there to convert this into percentage. 75. We've got 75.1. So I'm gonna delete again, guys. After that, we have to calculate what? Equivalent evaporation from an 800. I'm gonna delete this. I'm gonna delete this. Equivalent evaporation is equals to same story, mass of steam over H4 or H sub minus H1 over the mass of fuel multiplied by 2257. This was the value that was obtained when a boiler was tested, when let me say different boilers were tested, and 1 kilogram of mass was put into the furnace and then and bent, and when when that mass finished, the energy, when measured, the heat value or the heat transferred or the heat that was put into the boiler there, it was found to be 2257. That's basically, it was experimentally obtained, but let me not take that. And it is 6,500 over 2880, I think, 42 minus 158 over 620 multiplied by 2257. And we have 2880, 42 minus 158 multiplied by 6,500 divided by open brackets 620 multiplied by 2257 closing brackets. Answer. This is 12.6 kilogram of steam for every kilogram fuel. That's basically what this is. For every 1 kilogram of fuel, 12.6 kilogram of steam was produced. That's basically what that says. And then what? The temperature of the exhaust gas. The temperature of the exhaust gas. Very, very, very important. The temperature of the exhaust gas. The temperature of the exhaust gas. It says the heat added let's read it together. The temperature of the exhaust gas at the outlet of the economizer, if the inlet temperature of the economizer is 480, it's 480, straightforward, 480. The heat added to the economizer, the heat added to the economizer, the heat added to the economizer is equals to the heat received. It's equals to the heat received by that economizer, and I'm gonna show you how. Let me finish. Let's do this, guys. I think we are done here. I don't think I'm gonna need this. Right. Actually here, we've got what is so called a preheater, and it is divided by a plate. So when the air enters this plate, it is made hot by flue gases on the other side as they leave for the chimney. I don't know how to draw a chimney. Yeah, let's say this is a pipe or just a hole from there into the chimney. Right, this is a preheater. This is the air, this is the mass of fuel, and then this fuel produced a caloric value of, I think, 38. Right, now, listen to this one. Very, very, very important. They say the air entering there is 25 kilogram. Ne? If this air is not properly prepared, it's not properly conditioned for the furnace, it's gonna enter. Let's say for instance it becomes, normally a more colder substance absorb more heat, and now this air is gonna get into the furnace and mingled and mixed with the combustion products there, like heat for instance. So if it is not properly conditioned, it's gonna absorb more heat than the surface of the furnace, and then it does what? This is the pipe, remember, this is the pipe for the air, this, and then it goes into the combustion chamber. So when they mingled, it absorbed more heat, and then it was measured that the temperature of those fluid gases there is 480 degrees, and then they come and enter the economizer there. They enter the economizer there. So this heat added, it is actually the actual evaporation. Let me write it. The actual evaporation in mass multiplied by the caloric value. The actual evaporation in mass multiplied by the caloric value. It is the heat added there. Is equals to what? It is equals to mass of air multiplied by the specific heat capacity of air multiplied by the temperature. Changing temperature, 480 minus the required temperature. The required temperature. Look, the entrance there, practically speaking, the entrance there is 480. When it get out of the, when these fluid gases get out of the economizer, it should be less. That temperature should be less. Why? The water has absorbed heat from those fluid gases. Why? Because this temperature, the main source of this economizer is the fluid gases. It uses these fluid gases to hot up the water before it enters the evaporator or the boiler. Normally the evaporator is called the boiler. That's basically the case. And it is equal to what? The actual evaporation, they normally, I wrote there, but they normally called it mass. And it is equal to what? It is equal to 6,500 over 620 multiplied by the caloric value there, which is H2 minus H1, and it is, I think it's 318. Yes, 318 minus 158. Minus 158. This video is starting to get long, guys. 318 minus 158. It is multiplied by 160. So 6,500 divided by 620. Answer multiplied by 160. It is 1677,42 is equal to the specific heat capacity of air, the mass rather. It is 25 multiplied by, take it from me, the specific heat capacity of air is 1,005. I'm normally working with the International Engineering Council standards. Is equal to what? 480 minus T1. You want that temperature here after it has left the economizer before it gets out on the chimney. Let's divide by this. We've got this. I'm supposed to write it down, but I don't have space. It is divided by 25 multiplied by 1,005 is equals to 480 minus T1, and it's equals to 1677,42 divided by open brackets 25 multiplied by 1,005 closing brackets. Answer 66. let me write it here, guys. It's for you to see. Let me write it here. 66,76. This thing comes here. Is equal minus 480 is equals to minus T1. Okay, minus 480. Meaning we're gonna have what? T1 is equals to 413,24 degrees Celsius. There, the temperature there is 413,23. What does that mean? It means this water is absorbed how much? 480 minus 413,32. This water is absorbed roughly 66 degrees Celsius before it gets into the economizer. Hey guys, thank you very much, man. And this is actually not finished. This is easy. You can even be requested to draw the heat balance of this. You've got what? You've got the heat gained, which is roughly 38 megajoules. You calculate the energy absorbed by the economizer, by the evaporator, by that. And then you subtract them from this 38. The remaining is the excess energy. Is the excess energy that is left. Yes guys, thank you very much, man. I hope you enjoyed the video, even if it's long. But please, man, subscribe, share the video, and then also leave a comment there, and we'll see what we can do. Thank you very much, man. Bye.